So nucleophilic substitution involves the substitution with a nucleophile, and we commonly see it with halogenoalkanes and hydroxides. So very simple mechanism is with the reaction with hydroxide ion, it will form an alcohol. Okay, but we need to think about the primary, secondary, and the tertiary classification of the haloalkanes. Okay, because the mechanism goes in theory like this. So let's take this example of bromoethane. We have the carbon, which is our electrophile. Bromine is slightly negative. And we have the hydroxide, that is our nucleophile. So one important thing to consider is the direction of this attack, because it's called like backdoor attack, or it has to be on the opposite side of the bromine. Okay, so it can't be this direction. It has to be in the opposite direction. So there is a new bond formed between the oxygen and the carbon. And at some point, the carbon-bromine bond has to break. So this one-step mechanism, we have the substitution. I'm not going to talk about the change in stereochemistry. I think it's not relevant for the basics. But substitution is occurred in one step. This is called Sn2. Substitution, nucleophilic, true. True is because in the rate determining step, which is the step that affects the rate of reaction, we have both the nucleophile, because in this step, both of the nucleophile and the substrate, it's called substrate, the molecule that is reacting, they're reacting at the same time. Notice, so they're both present in this step. Okay, so revision of a little bit of kinetic rate, it's how fast the reaction goes. This is the rate equation with the rate constant. Check out the videos on kinetic if you want to learn more about it, but otherwise just think that in the rate determining step is the nucleophile and the substrate that are both present and react at the same time. Okay, this is Sn2. But the important thing for Sn2 is that there is a space for this to occur, because let's take, this is a primary haloalkane, let's take a tertiary haloalkane. Things are going to be slightly different. So tertiary, we have, let's take the simplest tertiary. Then let's say we have bromine. Now, the OH that has to attack on the opposite side than the bromine doesn't have space to do that, because there are all of these big carbon groups that cause this called steric hindrance. They don't allow the OH to attack directly on the correct orientation. So this works a bit differently, because the first step is actually this, that the carbon-bromine bond breaks. This would form a carbocation intermediate and looks something like this. So we have CH3. I'm going to change a little bit the shape, but I want you to really focus on the basics of the difference between the two mechanisms. So I'm not going to talk about intermediates very much or shapes, but we have this carbocation. And now, because this is also three, like it's planar, there is a space for the OH to attack, because there is more space now. Imagine this being planar, and the OH can attack like above and below this plane. So in this case, I just want you to think about that there is no more that hindrance that was preventing this Sn2 mechanism. But now the attack is in another step. So this occurs in two steps. If there are multiple steps, they can be all rate determining. So the one that affects the rate of the reaction is the first one. So this is our rate determining step. So the rate equation now only involves not the nucleophile, because the nucleophile is in the second step, but just the substrate. Notice there is one species in the rate equation, and that's why it's called Sn1. So the differences between Sn2 and Sn1 is that the Sn2 occurs in one step only. Both nucleophile and the substrate react at the same time. Sn1 occurs in two different steps. The reason why it occurs in two different steps is because it's more hindered, so the nucleophile doesn't have space to react with directly with the carbon, with our electrophilic center, the carbon. So occurs in different steps. And the main difference is that, this hindrance. So to summarize it very simply, if you have to identify like a multiple choice question, if it's primary, it's going to be Sn2. If it's tertiary, it's going to be Sn1. If it's secondary, it kind of depends, because notice that the nucleophile affects the rate of the Sn2, but doesn't of the Sn1. So if you have, for example, a very weak nucleophile, it's probably more likely to be Sn1 because it doesn't affect the rate anyway. So it depends a little bit on other things. Yeah, but to keep the basics very clear, Sn1 and Sn2, the main difference is primary substrate or tertiary substrate. Okay, so I hope that makes sense. Just to clarify it, secondary can undergo both. Yeah, it depends a little bit on the molecule, like how about like this concept of steric hindrance. But the biggest difference between Sn1 and Sn2 is the nucleophile. So if we have a secondary hydroalkane with a very strong nucleophile, probably it undergoes Sn2 because the nucleophile increases the rate of reaction because it affects that. If it's a very weak nucleophile, it's probably more likely to be Sn1 because the weak nucleophile doesn't affect the rate of reaction anyway. Okay, so in that case, it can be both.